Everything we've discussed so far, B trees, LSM trees, hash indexes, has been about primary key indexes, one unique value per row, and the index maps that value directly to the row. But most real applications need to query on many different columns. Not just find me user ID 42, but find me all users in Seattle or find me all orders placed on Tuesday. That requires secondary indexes, and secondary indexes come with their own design decisions. Creating a secondary index in SQL is as simple as running create index. But under the hood, secondary indexes have a key difference from primary indexes: they are not unique. Many rows can share the same indexed value. Every user in Seattle shares the same city value. Every Tuesday order shares the same day value. The index has to map one key to potentially many rows. The rows themselves are typically stored in what's called a heap file, a file where rows are stored in no particular order, as they were inserted. Each secondary index entry just stores a reference to the location of the matching row in the heap. When you follow that reference, you go from the index to the heap file to retrieve the actual data. When you update a value in a row without changing the index key, the heap file can often update in place as long as the new value fits in the same space. If the new value is larger, more complex handling is needed. A clustered index takes a different approach. Instead of storing a reference to the row, it stores the row directly within the index. MySQL's InnoDB always uses the primary key as a clustered index. Every row lives inside the primary key index. Secondary indexes reference the primary key value rather than a heap location. Between a pure heap file reference and a full clustered index, there's a middle ground, a covering index, which stores some columns from the row inside the index itself. If a query only needs the columns stored in the covering index, it can be answered without ever touching the heap file at all. The index covers the query entirely. These variations trade off write cost against read speed. Each is the right tool for different query patterns. Standard B trees and LSM trees are excellent for one-dimensional range queries: find all keys greater than X and less than Y. But some queries are inherently multi-dimensional, and for those, standard indexes fail in a specific and important way. Consider a map application. You want to find all restaurants within a rectangular area on a map. Translated to database terms, that means, find all rows where latitude is between 51.4946 and 51.5118, and longitude is between -0.1257 and -0.1022. This is a two-dimensional range query. Here's the problem: a B tree can efficiently execute a range query on latitude alone, or longitude alone. But combining them requires an additional filter. The database scans all rows matching the latitude range and then checks each one for the longitude constraint. For large datasets, this is expensive. What's needed is a multi-dimensional index, an index designed to narrow down both dimensions simultaneously. PostGIS, the geospatial extension for PostgreSQL, implements R-trees for this purpose using PostgreSQL's generalized search tree facility. R-trees organize spatial data so that nearby objects are grouped together in the index, making it efficient to find everything within a bounding box. Multi-dimensional indexes aren't limited to geography. A database of weather data might need to query by date range and temperature range simultaneously. A database of products might need to query by category and price range. Whenever your query spans multiple dimensions at once, a standard single-column index won't give you the full benefit. On the other side of the spectrum from precise range queries is fuzzy search, finding approximately matching keys. Search engines need to find documents matching a query even when users misspell words. The key word is within some edit distance of the search term. Lucene, the text search library underlying Elasticsearch, handles this using a finite state automaton over the characters in keys, which can be transformed into a Levenshtein automaton. A Levenshtein automaton efficiently identifies all keys within a given edit distance of the query term. This is a very different data structure from a B tree, purpose-built for approximate string matching. The pattern across all of these cases is consistent: different query shapes require different index structures. Disks have held a fundamental advantage over RAM for decades. They are cheaper per gigabyte, and they retain data when the power goes off. RAM is faster but expensive and volatile. That balance has been shifting. RAM prices have fallen dramatically. For many datasets, those in the range of gigabytes to low terabytes, the entire dataset can fit in memory across a cluster of machines. And when that's possible, you can build a database that never touches disk for reads. Memcache pioneered this, a purely in-memory key-value cache that offers no durability guarantees. If the process restarts, all data is gone. For a cache, that's acceptable. But several databases aim for both the speed of in-memory storage and the durability of disk-based storage. VoltDB, MAMSQL, and Oracle Times10 are fully in-memory databases that achieve durability by writing logs to disk and replicating data to multiple machines. Redis and Couchbase offer weaker durability by writing to disk asynchronously. The write is acknowledged before it hits disk, so a crash in a narrow window can lose recent writes. Now here's the counterintuitive insight that the book makes explicit, because most people assume the wrong reason for why in-memory databases are faster. You might think in-memory databases avoid disk reads, and disk reads are slow, so of course they're faster. But that reasoning is incomplete. A disk-based database with enough memory will also avoid most disk reads, because the operating system caches recently accessed disk blocks in RAM automatically. A busy database with a hot dataset can serve most reads entirely from the OS cache without touching disk. So why are in-memory databases actually faster? It's not about avoiding disk reads. It's about avoiding the overhead of encoding in-memory data structures into a disk serializable format. A disk-based engine must serialize every data structure, every linked list, every tree node, every hash map into a byte layout that can be written to disk and read back correctly. In-memory databases skip that entire encoding and decoding step. Data can be stored in whatever format is most efficient for the CPU, native pointers, flexible data structures, no serialization overhead. That's the real performance advantage. And it suggests that as RAM gets cheaper, the boundary between in-memory and disk-based systems will continue to blur.